Right. And why should our listeners care? Well, picture searching for a contact on your phone
Uh-huh.
or finding a word in a dictionary app. That's speed. That's sorted data.
It really is. Sorting is key for fast searching. We'll get to binary search later, which shows that perfectly.
Imagine a phone book with names just jumbled
Oh, a
randomly.
nightmare. You'd be scrolling forever.
Sorting makes it almost instant.
Transforms it completely.
Now, these notes, wow, it's like a list of sorting greatest hits, selection sort, bubble sort, insertion sort.
Merge sort, quick sort.
Radix, bucket, heap, even shell sort gets a mention.
Yeah, there are quite a few ways to do it.
We won't drown in the details of every single one today.
No, definitely not. We'll focus on a few key ones to, grasp the main ideas.
Okay, sounds good. Let's dive in with a real classic bubble sort.
Ah, bubble sort. It's probably one of the most straightforward.
How does it work, basically?
The core idea is simple. You look at two adjacent items in a list. If they're in the wrong order, you swap them.
Just neighbors.
Just neighbors. And you keep doing this through the list. The bigger values kind of bubble up towards the end.
I like that, bubbling up.
Yeah.
So let's trace it. Based on the notes, how would it handle actual data?
Okay, so imagine you have an array, let's call it A, with n numbers, A1 to n.
Right.
Bubble sort starts with the very first pair, A1 and A2. If A1 is bigger than A2, swap them.
Okay.
Then you look at the next pair, A2 and A3. Same deal, swap if the first is bigger.
And you just keep stepping through.
Yep. All the way until you compare the second to last and the last elements, N1 and N.
Got it. So after you've gone through the whole list once like that, what's the state of things?
After that first full pass, the single largest number in the entire list is guaranteed to be sitting in the very last position, Anne.
Ah, it bubbled all the way to the top. Or the end in this case.
Exactly. Like the biggest bubble reaching the surface.
So what next? Just start over.
Almost. You repeat the process, compare neighbors, swap if needed, but you already know the last element is sorted.
So you don't need to check it again.
Right. In the second pass, you only go up to comparing AN2 and AN1.
And after that pass.
The second largest element will have found its correct spot at AN1.
I see. So with each pass, one more element gets locked into its final sorted position at the end.
Precisely. And you keep doing this. The notes say after N1 passes, the whole array A1 to AN will be sorted, smallest to largest.
Your notes also show some pseudocode for this. Can we break that down?
Sure. It starts by getting the n numbers into array A, then it has an outer loop using I that basically counts the passes from 0 up to n1.
Okay, one loop for the passes.
Inside that, there's an inner loop using J. This one runs from 0 up to ni2. That ni2 part is because the end part of the list is already sorted after each pass I.
Right, so the inner loop gets shorter each time. What happens inside it?
That's where the comparison happens. It compares AJ with AJ plus 1.
Its neighbor.
Exactly. If AJ is greater than AJ plus 1, meaning they're out of order,
Swap them.
swap them. The pseudocode mentions using a temporary variable called swap to hold one value during the exchange.
Standard swap logic.
And once both loops finish, the pseudocode says display the sorted array A.
Now, the notes have these in example slides using 67, 45, 23, 14, 6, 33, 98, 42. They show every single comparison.
Yeah, those are super helpful visually. You can really track how, say, 98 moves rightward pass after pass.
And it shows the swap status for each step.
Right. It highlights exactly when elements trade places. We probably don't need to narrate every single swap here.
No, probably not.
But the key takeaway is seeing those larger values drift towards the end of the unsorted section with each complete pass.
Watching the bubbles rise. Now, you mentioned in optimization, the basic version sounds like it might keep going even if the list gets sorted early.
That's a great point. Yes, the naive version does exactly that. It runs all N1 passes no matter what.
Inefficient if it's already done.
Very. The optimization introduces a flag, let's call it swapped. You set it to false at the beginning of each outer pass.
Okay.
Then, inside the inner loop, if you do make a swap, you set swapped to true.
Ah, I see where this is going.
Exactly.
Yeah.
After the inner loop finishes, you check the flag. If swapped is still false, it means you went through the entire list without making a single swap.
Which means?
It's already sorted, so you can just stop the whole algorithm right there, break out early.
That's much smarter, especially for lists that are nearly sorted to begin with.
Definitely saves unnecessary work.
So, given its, let's say, performance characteristics, where would bubble sort actually be used?
You're right to question its performance. Its time complex generally ON2, which isn't great for large data sets.
N squared is usually the sign of a slower algorithm for big inputs.
It is, but bubble sort is incredibly simple to understand and implement, like really simple code.
Okay.
So you might see it used if the data set is tiny, where the overhead of a more complex algorithm isn't worth it, or in educational settings to introduce sorting concepts.
Makes sense. Or if the code simplicity is the absolute top priority.
Exactly. The notes say it's preferred when complexity doesn't matter, or short, simple code is the goal. And the optimized version isn't terrible if you know the data is almost sorted already.
Okay, let's shift gears. Next up, insertions.